Okay, so good morning, everyone. So today I would like to speak about the effect of supersolids. So what is a supersolid? Supersolid is basically something that is both a superfluid and a solid. So a solid, you more or less know what it is, you know, from your basic condensed matter physics courses. We will a little bit briefly also, I will also tell you a few things that are important for us in relation to the supersolid, to the solid. While the superfluid is an effect that we haven't discussed, that you probably are not familiar with. So I would like to spend the first part of this course speaking about superfluids, and then in the second part we will speak about the supersolids. Okay, so what is a superfluid? A superfluid is basically, let me share my screen. Okay, good. So you can see my screen. So we would like, so let's first discuss what is a superfluid. So a superfluid is basically a Bose-Einstein condensate plus interactions. Okay, it's an interacting Bose-Einstein condensate, and as we will see, the properties of the superfluid and presence of interactions are quite different from those of the BEC, and we will discuss that. So the basic model that we need to discuss is just a model of three bosons plus an additional interaction term. So we can write an Hamiltonian, which is just the Hamiltonians of three bosons. That's something that we have already seen. So there is some integral in space times some psi dagger dx squared. Okay, so this is basically the kinetic energy, if you want, -1/2m times psi. Okay, so this term here is just the kinetic energy, plus some interaction term. So in the interaction is basically proportional. You can think of it as something that is proportional to the number of particles squares in a given place, right? In order to have an interaction, so you can write it as basically u times n squared, again integrated over x. Okay, and of course, usually it's actually defined as u/2 n squared. The reason is that the number of the interactions is proportional to the number of pairs that you have. The number of pairs is roughly the number of particles squared divided by 2. So this is basically interaction. And for what we are going to discuss, we are actually going to consider a system in which yes, okay, so good. So this is the Hamiltonian of the system, and let's try to discuss what are the symmetries of this Hamiltonian. Okay, I just recall that what is nx, and s is a psi dagger of x, psi of x. This is the number of particles. Okay, so what are the symmetries of the problem? Any idea from the audience? There are two basic symmetries in this Hamiltonian. But there are many, but
there's U1 symmetry.
Yes.
Any phase to psi.
Yes. So there is a UN symmetry. The UN symmetry, it's basically related to the fact that the number of particles is conserved. Okay. So if I define n, which is the total number of particles, so it would be just an integral over n of x. Okay. This is a conserved quantity because particles are not created or destroyed from the vacuum. So what we need to have is basically h n equals to 0. So n commutes with h. And okay, so I'm glad that my computer is back, so I can compute. Okay, so that's one symmetry, and this is indeed associated with this phase, this gauge invariance. So if you take, it is associated with, if you take psi that goes psi e to the I theta. Okay, so if you multiply psi by some constant, this is also a conserved quantity. So you can see that there is some relation between the number of particles and the phase. Okay, we are going to discuss that later in more details. But for the moment, these are like two independent ways to we will see that they are actually why they are strongly related. But for the moment, we see like two possible ways to describe the conservation of total number of particles, either as the Hamiltonian conserves of n, or the fact that if you take psi that goes to psi to the I theta, and say psi dagger goes to psi dagger e to the minus I theta, then you see that the Hamiltonian goes to itself. Okay, so this is another way, and that's why this symmetry is called the U1, because a phase, it's just a continuous variable, one continuous variable, so it's called the U1. And actually, it's a periodic continuous variable. So this is basically the definition of U1. Okay, good. So which other symmetries do we have?
Well, I guess
Translational symmetry, very good, yes. Okay, translational symmetry. Any more? Actually, there's at least one more that I can think about.
Maybe SU2, if we have particles with spin.
Okay. Okay, so you should now see me from here. Okay. Very good. 1 second. Okay, good. Yes. So if there are particles with spin, yes, but these are spinless particles. Okay, so that we don't have any spin. Maybe just this is just, the assumption is that these are just spinless. You're right that if we had the spin, then then this would be that there could be an SU2 symmetry, but here there is none. So I think another symmetry that we can have is basically an inversion symmetry. If you take x that goes to minus x, this could be this gives rise to some inversion symmetry. Okay, so whenever you have a symmetry, you can break it. You can spontaneously break it, and this is exactly okay. Sorry, okay, good. Okay, nice. Okay, cool. Now you should be able to also to see me. So whenever there is a translation, whenever there is a symmetry, you can spontaneously break it. So if you spontaneously break the translational symmetry, that's what we call a solid or a lattice, right? A solid is something that breaks the translational symmetry because initially the space was translational invariant, but then you have particles that sit at regular different distances from one to each other. So you break the translational symmetry is now broken. Or if you break this number of particle symmetry, this human symmetry, what you get is a superfluid. Okay, so this is a nice way to understand what a supersolid would be. So a supersolid would be a phase in which both symmetries are broken. Okay, and in principle, at least theoretically, this is something that is plausible. I mean, you have two different symmetries, and you break both of them. Okay, the inversion symmetry. I mean, actually, I don't know whether one can. I mean, for sure, one can spontaneously break it, but I don't know what this could. What this would give rise to. Okay, so what we would like to discuss now is some description. So we would like to describe the properties of the superfluid, and the way that we are going to do that is by introducing some mean field approximation. Okay, with mean field approximation. So in the mean field approximation, what we assume is that instead of having psi that is an operator, we substitute it by some just a constant. Okay, so instead of having psi operator, we have some constant. So I call it psi bar. Psi bar means that this is just a number. And what you see, what happens with the Hamiltonian? So the Hamiltonian now becomes h. So as you can see here there is the derivative in space. So if psi is a constant, and let's assume in the simplest case it's just a constant. You know, it's a constant in time and space. So this time derivatives give 0. So the kinetic energy is 0. And what you are left with is just the interaction term. Okay, so what you obtain is basically 1/2, probably v over 2, the integral over the volume. times, let's call it, I prefer to call it actually G, this interaction term. So V over 2, G times psi bar to the. So let's for simplicity, let's assume that psi bar is a real number. I mean, this is not just will make our life simpler. And as it was discussed, because there is a symmetry, so I can always choose a psi in such a way that it is real. Okay, now in order to proceed, so what we would like to do next is consider the fluctuations. Okay, so we would like now to add fluctuations. As we will see in a moment, the fluctuations actually basically break the symmetry of the conservation of the total number of particles. We will see that in a moment. But we know that originally there was that symmetry. So we need to do the mean field in such a way that we sort of remember about the conservation of the number of particles. And the way to do that is that instead of looking at the Hamiltonian, we look at the free energy H minus mu n. Okay, so we add basically this Lagrange multiplier. If you want, we move to the macrocanonical ensemble, or in other words, we add the Lagrange multiplier that will help us setting a constant total number of particles. Okay, so that's why I move from the Hamiltonian itself to the Hamiltonian's minus mu n. If I had just the original Hamiltonian, because the total number of particles is constant, then just adding mu times n is just like adding a constant to the Hamiltonian. So it does absolutely nothing. However, in the case of the mean field, as we will see, because the mean field approximation breaks the symmetry, it is important to recall that the total number of particles must be conserved. And so that's why we multiply this, we add this minus mu n. Okay, so again, the mean field, okay, good. So what we obtain in this case, what is actually n? So n is basically the volume times psi square. Not even the absolute values. We said psi is going to be real, so the volume psi square. So that means that this free energy F is going to be V over 2 times G psi bar to the fourth minus mu volume psi bar square. Okay, and so in order, you need to minimize the free energy, so you need to have dF over the psi bar, which is going to be 0. And so this condition requires that basically Vg psi bar. So we take the derivative of f with respect to psi bar. So this gives us 2 actually, right? This 2 Vg psi bar cube minus 2 mu v psi bar. This should be equals to 0, and therefore this can be used to derive what is the chemical potential mu. So the chemical potential mu is going to be just G psi bar squared, which is just G times n. Okay, and as you remember, n is defined as psi a psi Dagger psi. So if you want, this is basically n bar, right? N bar is just a psi bar square. Okay, so we find that the chemical potential is this coupling, this interaction term G times n bar. Okay, and you already see that something unique happens when there is no interaction, then the chemical potential is exactly 0. Okay, that indeed, if you remember, this was indeed the case of the Bosons condensate. If you remember the derivation, I'm assuming that you have all seen that in some previous course, the derivation of the Bosons condensation. In that case, the chemical potential in the BEC was exactly 0. And here what we see is that due to the interaction, the chemical potential becomes finite, and we will see that has some important consequences. Okay, good. So this is in terms of the mean field. But in order to study, say, the dynamics of the problem or the physical properties of the BEC, of the superfluid, what we need is to study what happens, what are the effects of the fluctuations. By the way, how many of you have already seen this derivation? The derivation of the fluctuations in the superfluid. Basically, we are going to derive the Bogoliubov excitations. of the model? Okay, Yaakov, of course. Okay, seems like the other haven't, so that's good. Okay, so we now want to discuss the fluctuations, how you do that. The way that you do that, it's like the standard way. So you say there was the psi operator, and now I'm assuming that the psi operator is going to be the psi bar, the average value, plus some fluctuations. So for convenience, I would like to call the fluctuations phi hat or phi. Sometimes you call it a delta psi, but just I don't like delta psi because these are two symbols, so it's more expensive. So I just call phi. So phi is going to be the fluctuations of psi. Okay, so what you need to do now is to take your Hamiltonian, okay, you take the Hamiltonian, and then the Hamiltonian was this one, okay, and then you substitute this psi bar plus fluctuations. So what happens to the first term when we do that substitution? Okay, you can guess. I mean, this is a question for you. So I'm taking this part of the Hamiltonian and substituting psi bar, which is some constant, plus phi. What happens?
You get the same term, but with phi.
Right, exactly. So I'm left only with the term that is is with the same Hamiltonian basically. So I'm left with d free x of phi hat derivative 1/2m phi hat. So it's just the same term because the constant part falls off. Okay. Now you may ask, what about the linear term, right? So in principle, you should have also a linear term, something like phi bar, say phi bar to the left times the time derivative of phi hat. But this term is the total derivative of something, right? It's the derivative of phi hat. And so this is a term that you can basically integrate out. I mean, when you can integrate by parts and you see that assuming that in long distances, the phi hat goes to 0, then this term vanishes. Okay, so in general, these linear terms fall off. Okay, so that's what you get from here. How about the other terms? So what we have, remember that we are looking actually at h, which was h minus mu n. Okay, so plus what you have here, so you have here basically phi times minus mu times n by n. And n, as we discussed, is basically psi bar plus phi hat square, okay, minus g, same term, phi hat plus psi bar plus phi hat to the fourth. Okay, so these are the other two terms. So let's open up the square. Okay, so what we obtain is, and there was here a plus. So you have minus. Let's now focus only on this part. Okay, so only on the interaction part. So let's call it H interaction. So it's minus mu, and then what you have is psi bar to the square plus phi squared plus twice psi bar phi hat. Okay, like this, plus g times. And here you have, okay, you have to open up this fourth order term. So you have a psi, okay, you have psi bar to the fourth plus psi bar, free psi bar that multiplies, sorry, four phi bar that multiplies, there was 1/2 here, this is going to be important, that multiplies phi hat, right? Plus there is a 6 psi bar square phi hat square. Yes. And then you have other terms. So the other terms, I'm going to neglect them. Why? Because the other terms are going to be proportional to phi cube and phi fourth. And so what we are going to do is an approximation, okay? We need to do some approximation. Until this point, everything was exact. But at this point, I'm going to neglect those terms because those terms are proportional to phi hat cube and phi hat 4, and we are going to neglect them. Okay, so we neglect this term. This is the approximation. So what do you obtain? So we obtain something like, so first of all, you see that these two terms cancel. I mean, so remember, actually, no. So let's have a look at these two terms. So what they give us, okay, so we have minus mu plus 1/2 g, okay, times phi bar square, square, okay. So this is the first two terms, okay, the terms that are, I'm taking together the first two terms that are not, they do not depend on phi, right? This term and this term do not depend on phi, these two terms, so we put them aside. Then we have terms that are linear in phi bar. So the terms are minus mu plus 1/2 g times 4 times 4. No, wait a second, sorry, confused a little bit. So again, now I need to take the terms that are linear. So I want to take this term and this term, okay? So we have plus minus mu plus 4, oh, this is cube, phi, this is cube. Times psi bar 1/2 psi bar square times phi hat. Okay, so do we agree? These are these two terms, the terms that are linear in phi bar. So this term and this term. Okay, plus what we have is basically 3 times g phi bar squared phi hat squared. Oh, and there is a 2 here. Here there is a 2, because this is this 2 here that comes here. Okay, so what happens? So the first term, okay, the first term gives you some constant. So when you're studying, it's just a constant. So again, this is like adding a constant to the Hamiltonian. So that's not important for the moment. What happens to the second term? Remember that this was mu, right? We have found mu. So what happens to the linear term? I'm of course missing a g here. Okay, now it should be fine.
Goes to 0?
Yes, exactly. So this term is equals to 0. Okay, this is quite generic. Every time that you do a mean field, basically what you are doing, you are looking for the minimum. So that's why the way, if you see, the way that we derived mu was exactly by demanding that so we are looking for the minimum. So the psi bar is chosen in a way that psi bar is the minimum, is the local minimum of the energy. That's why the linear terms are 0. Okay, this is because we are looking at linear terms. And then what we are left with is those terms here. So what we are left here is this quadratic term. So let's summarize what we have seen. So the Hamiltonian is now has the following shape. So it's an integral over space of phi hat, okay, times minus second derivative 1/2n, like this, phi hat, plus 3g mu psi bar squared phi square.
Isn't there
let me just 1 second. So we need to do it a little bit better. And the reason we need to do it a little bit better is that actually So here I have done some, have messed it up a little bit. So let me redo this part here. This is actually, I forgot about the fact that, I mean, psi bar is a real number. However, phi hat is an operator. And actually what we really have here is not phi, it's not, this would be psi to the fourth, but what we have is psi dagger psi, psi dagger psi. Okay, so let me redo it here. So I want to discuss this term again. This is actually this was sort of qualitatively, but if you look at that exactly, what you should have is basically psi bar plus phi, psi bar plus phi, psi bar plus phi, psi bar plus phi, with dagger and dagger. Okay, so that's actually a better description of what we have here. Because we need to remember that phi is a non-Hermitian operator. Okay, so once you understand this point, you see that what are the quadratic terms? So the quadratic terms are something that is proportional to psi bar. You're looking for terms that are proportional to psi bar square. And what are those terms? So there is a term that looks like basically phi dagger plus phi square. Okay, there are sorry. Okay, so there are the phi couples both to psi couples both to phi dagger. Okay, so what you really need, what you should really have here is actually right? So G times phi bar squared, phi hat plus phi dagger square. Okay, so that's what you obtain from this derivation. Actually, there is even a 1/2 here. Does it make sense? What I'm trying to say is that the interaction term is basically phi squared times 4 terms. There are 4 terms, which are psi dagger square, phi dagger square plus phi square plus phi dagger phi plus phi dagger. Okay, in this quadratic in the quadratic approximation, we have those 4 terms, which we can summarize in the way that I've written here. We can now move to momentum space. Okay, let's now move to momentum space. So what we obtain is basically phi hat q minus q squared over 2m plus q squared over 2m phi q plus 1/2 g phi bar square. Now remember that psi bar is a constant. So when you Fourier transform it, nothing happens to it. This is just a number, it's a constant. Okay, if you want, remember also that what was g psi bar squared?
Mu.
Mu, exactly. So this is mu. And here you have phi q hat plus phi q dagger square. Okay, so what you see is that now the Hamiltonian, we have obtained an Hamiltonian that is decoupled. So we have decoupled, these are all. What we have here are decoupled harmonic oscillators, right? Because it's a quadratic Hamiltonian for each independent q, for each q independently. Okay, so if you want, you can also rewrite this in this form. I can write it as sum over q, phi q dagger phi q, phi q dagger phi q. And what we have here, so it's basically 1/2 mu 1/2 mu. I think probably here that it should be, I think there is no 1/2 here. If you do it properly, I think there is no mu. So you have mu plus q squared over 2m. You have mu, and mu plus q squared over 2m. Okay, right? And now when you look at this, you know what we need to do. So how can we diagonalize this Hamiltonian? How can we find the eigenvalues of this Hamiltonian?
So by Bogoliubov rotation?
Yes, exactly. We need to do a Bogoliubov transformation. This is exactly, if you have done the homework, this is exactly what you have seen, right?
Yeah, sorry. So I think so you write this Hamiltonian as a matrix, right? I think like the first
yes.
Column should be a row, so it should be like transposed.
That is very right. Yes, this should be like this. Okay, now it's better. Okay, very good. So what you have here is basically just a 2x2 Hamiltonian in which the operators are phi dagger and phi. So you cannot just do a perturbation. What you need to do is not just a regular rotation. You don't need to rotate. What you need to do is what is known as a symplectic diagonalization. What does it mean? You need to rotate phi and phi dagger in such a way that the commutation relations are preserved. Okay, so I just briefly mentioned this, that what you're going to do is to define some phi tilde, which is some u phi phi plus v phi dagger. Okay, so this is the transformed Hamiltonian, which is a sum over these two. Okay, so you do just a linear transformation, but the linear transformation is such that it's not that u squared plus v squared is 1, but in order to preserve the commutation relation, what you need to have is u squared minus v squared equals to 1. Okay, so this is, by the way, very much related to the presentation by Yakov last week. Okay, he also had this sort of conservation of the difference between the two channels. If you remember, in parametric oscillation, this is a conservation of the difference between the channels. This is exactly related to the fact that the parametric oscillator creates basically a squeeze state. Okay, a state in which you have also these phi and phi dagger terms, and this is something that conserves the difference. And this is in this language, it just means that the transformation that you need to do is a symplectic transformation. Okay, it's not a rotation. You don't need to rotate in the phase of phi and phi dagger, but you need to do a symplectic rotation, one that preserves this u squared minus v squared. If it was u squared plus v squared, then this would be just a unitary rotation, just a normal rotation that just a rotation that preserves the components of the x and y in the x and y direction. But this is a more complex rotation. It's called the symplectic rotation. By the way, if these were fermions, then what you need to preserve is the anti-commutation relation. And in that case, u squared plus v squared equals to 1. So if you have a sort of a pairing Hamiltonian of bosons, it's a symplectic rotation. And if you have a pairing Hamiltonian of fermions, it's just a normal rotation, just a u squared plus v squared equals to 1. Okay, so this minus has to do with the bosonic. Okay, so now you have done it in, I'm sure you have all seen already Bogoliubov transformation in the past. Let me just mention one fact which is important for me now, which is that actually this is equivalent to diagonalizing this matrix. So this is just a trick. So you can either do the symplectic rotation, or you can say that this is equivalent to diagonalizing in a normal way this matrix here. Okay, so you basically, what you do, it's a nice trick. What you do, you plug a minus here. Okay, you plug a minus in the two last rows, and this gives you another matrix. And so it comes out, and this is an exercise one can show, that doing a symplectic diagonalization of this matrix is exactly the same as doing a regular, in terms of the eigenstates, in terms of the eigenvalues, is exactly the same as doing a regular diagonalization of this matrix. Okay, so this is just a trick. And so now we can find the eigenvalues. So the eigenvalue expression is basically lambda minus mu plus q squared over 2m. Okay, this times lambda minus plus mu plus q squared over 2m, right? And then you have here plus mu squared equals to 0. Actually, it's minus mu squared equals to 0. Okay, or in other words, lambda equals to, so lambda squared, what we have is that lambda squared minus mu plus q squared over 2m squared equals to mu squared, or lambda equals to the square root of mu plus q squared over 2m squared minus mu squared, which is also equal, you can open the parentheses, and what you see is that equals to q squared over 2m plus mu q squared over m. Okay, so these are the eigen the eigenenergies of this Hamiltonian. Okay, and this is called, these are called Bogolyubov spectrum. Why spectrum? Spectrum just means that this is a function of q. Okay, so for each q you have a different energy. So we can call this as epsilon q. This is the energy as function of momentum. So we have excitations with a given momentum q, and this is their eigenenergy. Okay, now the Bogolyubov spectrum has two interesting limits. There is the limit of epsilon q, where q goes to infinity, say, when q is very large. What do you obtain in this case? Okay, here I'm missing a square. What do you obtain in the case where q is very big?
Free particle.
Yes, exactly. So if q is very big, then this is q to the fourth. So this term is winning. And while this term is q to the square. So we can neglect these terms, and we take the square root, and what you obtain is just q squared over 2m. So these are just the energy of the free particles, right? The kinetic energy of free particles. The other limit is epsilon of q going to 0. So when q is very small, you do the opposite. So you neglect this term, the q to the fourth term, and what we are left is square root of mu divided by m times q. Okay, so it means, if you want the absolute value of q, so that means that the low energy fluctuations of the superfluid are different than the case of the BC. What are the low energy fluctuations of the BC? Well, the low energy fluctuations of the low energy excitation of the BC is just to excite particles, right? In the BC, you have all the particles in momentum 0. If you want to create an excitation, you're taking one particle from momentum 0 to some finite momentum, and these are the free particles. So in the BC, okay, the energy in the BC is just q squared over 2m. These are just free particles. And indeed, this is also in the superfluid at very high momentum, at very large energies. However, at the small momentum, at low energies, the behavior is different. Okay, so, and the behavior is linear. So if I try to plot this, okay, so this is now q, and this is epsilon of q. So it's linear and then quadratic. Okay, so this is for the superfluid in presence of interaction. In contrast, if you had just BC of free particles, you would have just a q squared. So it would be something like this. Okay, so this is instead for a BC. This is just q squared. Okay, q squared over 2m. Now, from the plot itself, it's not clear how important it is. What's the big difference? What's the big deal? After all, at large momentum, it's the same. But it turns out, and that's something unfortunately we don't have time to discuss, but it turns out that the fact that this spectrum is linear, that's what makes the superfluid a superfluid. So what does it mean, superfluid? Superfluid means that it's a fluid without friction. And there is a criterion, it's called the Lambda Criterion, which tells you that if the spectrum is linear, then you have no friction. Again, in the course on ultra-cold atoms, I expand on this topic more. Okay, so just remember that this linear dispersion is very important. Okay, good. So there is another way to obtain the same spectrum, and this is something you're going to do in the homework. Okay, homework. and which is sort of an approximate way to obtain at least the linear part of the spectrum. Okay, so this linear dependence of the energy on modulus Q. And the idea goes as follows. So what you observe is that, so what you, the way that the homework is developed is the following. So you basically do the following. You assume that psi, you first define a phase operator. Okay, so we define a phase operator theta. Okay, and this approach is also going to explain us a little bit better this what we began, what the place, our starting point. So remember, the starting point we had that the conservation of the number of particles was related to this gauge U1 symmetry. This theta goes to theta plus theta 0. Okay, so what you do is define a phase operator, and then you do the following. You assume that psi, okay, psi is an operator. You assume that psi operator equals to e to the I theta hat. Actually, if you want to be more precise, let's call it psi bar, some constant, times e to the I theta hat. Then, after you do this, what you observe is that having done this definition and using the fact that psi dagger equals to 1, this is equivalent to, it's equivalent to theta hat and n being equals to I. Okay, that's something you're going to see in the homework. It's very simple. Again, it's a simple derivation. I can show it here, but I think it is more useful if you see it on your own. So the idea is the following. You first define the phase operator theta, which is defined like a phase. Okay, so the psi operator is e to the I some theta operator. And then what you observe is that the commutation relation, the canonical commutation relation can be rewritten as a commutation relation between theta and n, such that the commutation relation between theta and n equals to I. So what does that mean? What this means is that theta and n are a canonical conjugate one to each other. Okay, and then you can use this this observation in order to obtain the Bogoliubov spectrum. That's what you're doing in the homework. What I would like to do here is to give you some intuition of why is that. So why is theta the canonically conjugate of n? Yuda, Yaakov, what do you think? Why is, in what sense theta? How can we see that theta is the canonical conjugate of n, apart from the fact that it comes out of the calculation?
I think it's connected to the uncertainty relation, right? So if you know the phase, you don't know the number of particles.
Right. So that's something we probably all heard about, the fact that phase and number are canonical conjugate. But what is why is that? Why are they? Why is this relation true? So there are different ways to derive it. Sometimes you can do it using path integrals. But let me show you the way I would like to propose you to think about this problem, because this is a very important concept. The fact that phase and number are canonically conjugate is something that comes out very often in quantum optics. So let me explain to you in this way. Let's now think of what are the eigenstates of n. So the eigenstates of n are the Fock states, right? The state with a given number of particles. So n. Okay, these are just the eigenstates of n. What happens if we apply psi, say psi dagger to n? What you obtain, right? What is psi dagger times n?
Well, it's creation operator, so you get like as usual square root of n times n plus 1.
Exactly. So square root of n plus 1 times the state n plus 1. So this is roughly, you can think of it as a psi absolute psi bar, right? So remember that n right? N is approximately psi bar square. So the square root of n is approximately psi bar. Maybe, well, let's do it with the -1, so it's even nicer. So let's do it. Let's apply psi, the psi dagger. So what you obtain is a square root of n. So square root of n is basically psi hat, psi bar times n plus 1, n minus 1. Okay. But as we defined it, what according to the definition of a phase, this was also psi bar e to the I theta n. Okay, and this equals to psi bar n minus 1. So in other words, what we have here is that e to the I theta n equals to n minus 1. Okay, when I apply the phase, what does the phase operator? The phase operator moves n by 1. Now, so what does this mean? This means that theta, or if you want, e to the I theta is the displacement in n space. So if I think as n as my physical space, so let's think of n as being x. Okay, so this is my coordinate. And what I'm telling you is that e to the I theta, okay, equals to x minus 1. But this is exactly, right, like doing, is exactly like in the case of position and momentum, right? What does it mean to a shift operator is e to the I times the time derivative. Right, so this is exactly as saying that x and p are canonically conjugate to each other. So the phase theta, or the exponent of theta, shifts n. Okay, it is in the same way that p shifts x. If you apply the operator p, you are shifting by you're shifting by x. Okay.
So in the language kind of group theory, you would say that theta is the generator of particle number fluctuations or something like that, right?
Exactly. So when you take e to the I times an operator, that's so where e to the I, the generator of the symmetry, it gives you a shift. Okay, so this is exactly like here. You can generalize it. You can say e to the I PA x equals to x minus a. By the way, this is also, you can also invert, maybe you're not familiar with this notation, but you're for sure familiar with the other notation, which is that e to the I x p0 at x on some p equals to p minus p0. Yeah, this is, okay, here there is a plus, right? So in the sense, x and p are canonically conjugate to each other. So you see that if you multiply the p state with e to the I x0p, what you obtain is the state p plus p0. Okay, so this is maybe this is more, you're more familiar with that, right? The state p is e to the I xp. So if I multiply by e to the I xp0, what I obtain is the state p plus p0. Okay, right. So this also explains us. So first of all, I'm introducing this because this is very important in general. It's a very common language. You will use it in the homework to derive the Bogoliubov spectrum, and it also connects back to the beginning of the lecture. So let's go back to the beginning of the lecture. What I told you is that the Hamiltonian is there is a symmetry, is a conservation of particle symmetry, which we can also restate as the saying that if I multiply psi by some e to the I theta naught, the Hamiltonian remains the same. So think of it as the translational symmetry. So what does it mean? So you can think of n as being the momentum, as theta as being the position. So what I'm telling you is that the fact that the Hamiltonian is symmetric under translational symmetry, this is not translation, it's a translation in phase, okay? Translation in phase means that there is a conserved quantity, which is the momentum, and the momentum is canonically conjugate. So the fact that you are translational invariant in phase means that there is a conserved quantity. And the conserved quantity in this case is the momentum, which means the canonically conjugate of theta, which is m. Okay, so if the Hamiltonian is symmetric under translation in phase, then there is a conserved quantity, which is the momentum in phase, the momentum of the phase, which is the number of particles. Now, what is the only difference between phase and position?
Phase is finite over the range of 0 to 2 pi.
Exactly. Not only finite, it's periodic. So the phase is periodic between 0 and 2 pi, while position in general, it's not. And so what is the consequence in terms of the momentum? So the momentum in the momentum of the phase is discrete. Okay. You also know that if you take periodic boundary condition in space, what you obtain is discretized momentum. Right? Momentum is discretized if you have periodic boundary condition. So in the same way here, because the phase is periodic, then the canonically conjugate is discrete. So that's why the number of particles is discrete, because use is periodic. Okay. So what you need to define is not only the fact that how they are related one to each other, but it is also important to understand what are the sort of how you close these boundaries. Okay, nice. So I think we have succeeded in learning some basic stuff in physics, and again, this is a language that is very common in quantum optics. So in the words of quantum simulations, this phase and density point of view. Let me check my notes. I think what I wanted to, if I said everything I wanted to say. Okay, yes. So okay. Let me now spend a few words on solids. I spoke about superfluid. Now let's speak about solids. So in a solid, what you have is basically there is also a broken symmetry, and the way to and associated with the broken symmetry, there is an order parameter. So the order parameter of the superfluid was, if you remember, psi, right? This is a psi hat. Okay, this was the order parameter of the phase. And in the case of the solid, what is the order parameter? So in the case of solid, you have a density that is periodically oscillating. So in a solid, what you have is that n is going to be some n bar times cosine of q naught x. Okay, so q naught is the period of the lattice, 2 pi over a of the lattice, plus some phi. And I see that this solid breaks the translational symmetry because I can pick up a specific phi, right? When I pick up a specific, what does it mean to change phi? When I change phi, I'm basically moving my lattice, right? I'm moving, say, let's say that the maximum is where the atom sits. So by moving phi, I'm moving the lattice. And that's the symmetry that is broken so we can define what I'm mentioning this point because one can define a complex order parameter in this way by saying that actually, say, n of x is equals to some n bar e to the I phi bar times e to the I q naught x. Okay, plus emission conjugate. Okay, so there is a complex order parameter which has an amplitude. So the amplitude of the order parameter tells you how much oscillations do you have. So you can have, you see, we always think of a lattice in the sort of in an extreme limit where you have just a particle that sits there. So what we think about as a lattice usually is if this is space and this is m of x, we think of like delta functions. Right? This is a classical lattice. This would be a classical lattice. But in quantum mechanics, you know that there are fluctuations. So the particles are not fixed at a given place. So due to the quantum fluctuations, what you really have is more like something like this, right? So the density oscillates. The density oscillates with respect to some average n bar. So there is some average n bar, and the density fluctuates around it. But important part is the fluctuations have some amplitude. Okay, so there is an amplitude. This could be our say delta n. Maybe I think I should have it. Should have done a little bit in a different way. So maybe let's do it like this. Plus some n bar n0. Okay, so n0 just the average density, and there are some fluctuations. Now the fluctuations have an order parameter that is constant, which has a amplitude and a phase, and the phase tells you where do I put my. So this would be basically our phi naught. Where do I put my lattice? How do I break my symmetry? And what you see here is that also here now this phi hat is also periodic. So once you have chosen a specific Q0, so a specific periodicity for your lattice, then the way where you place the lattice is actually also periodic. Okay, and this is indeed, as you all know, the momentum, right? The quasi-momentum is periodic. Okay. Is this clear? What I wanted to say is that you can think of a solid also as a phase that breaks a spontaneously break a symmetry, translational symmetry, and it has a complex order parameter. What is the difference? The difference is that the density, the order parameter is associated with the density. Okay, so what is fixed here is the density, while in the superfluid, what was fixed was the phase. And in a sense, this also tells you why it is not easy to find a phase that breaks both that is superfluid, because in the that is supersolid, because in a supersolid you would need to both have a broken phase and a broken density. So you need to somehow fix two order parameters that are almost canonically conjugate to each other, where they're not really canonically conjugate. The reason is that the density of the solid is at a finite momentum. So it's not the density at zero momentum. That would be impossible. If you fix the phase at zero momentum, then you cannot fix the number because they are canonically conjugate. However, in this case, at least theoretically, it is possible to fix the density because this is a finite momentum density. So in principle, it is, at least in the theoretical model, it is possible to break both the zero momentum phase, okay, that would be the superfluid, and the final momentum density, which would be the solid. So this would give us a supersolid. Okay, let me just write it down. So the supersolid would be a phase in which you have you break theta at q equals to 0 and n at q different than 0. Okay, you break you have a fixed phase over the whole lattice, over the whole supersolid, and you have a fixed density order parameter. So the density oscillates with some given periodicity. That's written. Okay, questions? Okay, so if there are no questions, I suggest we take a 3 minutes technical break, and then I will show you some presentation, with some experimental results on the supersolid. I will try to convince you that the supersolid indeed exists. So let's take a 3 minutes break, and we'll reconvene. Okay, so let's continue our discussion. I'm going to share my screen now. If you would like to turn on your camera, then I know that you're back. Okay, good. So first of all, I have an important note. So I have discussed about interacting bosons and this course, and I have mentioned ultra-cold atoms, but I would like to say that the first time that the superfluid was observed was not with ultra-cold bosons, but rather with another type of bosons, which are helium-4. So helium-4 liquefies at a very low temperature, about 4 Kelvin. And when you continue to cool it down more and more, at some point it was observed that the specific heat as a function of temperature has what is known as the lambda transition. So on the right, so what you see, the reason it's called lambda transition is because it has a shape of lambda, and it's just a function that coming from high temperature, diverges at some critical temperature around 2 degrees, and then again goes down. So there is this divergence, and you're familiar with the fact that these divergences, a divergence in the specific heat is an indication of a phase transition of the second order. And in this case, the transition of the second order is between on the right hand side the liquid, so liquid helium, and on the left hand side the super liquid or superfluid helium. And okay, here these are data where you just zoom in and you see nicely these divergence. By the way, this is unique to helium-4. If you had helium-3, then this would not be the case. Why? Apart from Yaakov. Why helium-3 does not become a superfluid?
Fermions?
Yes, exactly. Helium-3 is, it has an odd number of particles, and hence it's a fermionic, and as a consequence, it does not become superfluid. It's not a boson; it's a fermion. Okay, good. So there is a 1 minute and a half movie from BBC about this superfluid helium. Let me share it with you.
Surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
Okay, that was a nice movie. See how? Okay, yes. Okay, so as we discussed, the physics of superfluid is related to this Bogoliubov transformation or to the presence of Bogoliubov excitations. Again, we haven't explained in detail, but the linearity is really the linearity of the slope that leads to the development of superfluidity. And in these experiments, in the context of quantum simulation experiments with record atoms, we were able to probe this spectrum. So what I'm showing you here is it's an experiment in the group of Nir Davidson about a decade ago. In the x-axis you have k, which is the momentum, and in the y-axis you have omega. And these dots, so forget about the insight. The insight is just a zoom in on this small momentum part, and you can really see that this is exactly the plot that I've shown you on the board before. So for non-interacting particles, this would be the dashed line. Then you would have a parabolic potential, so just k squared over 2m. While in the presence of interactions, instead, what you observe is a linear. Here you can see more zoomed in. So at large momentum, it's about the same. It's still k squared over 2m. But at small momentum, it's a linear dispersion relation. A linear dispersion relation in the relation between energy or frequency and momentum. And there is a sort of a crossover between some linear slope, linear behavior at small momentum and the quadratic at a large momentum, and this is called the psi, and it's related to the chemical potential. So the more interactions you have, the more this is shifted to the right. So the more it's linear. If the interactions are very weak, then it is only at very, very small momentum that you see a linear dispersion. Okay, nice. So the question now is whether one could observe a supersolid. So first, I'm going to show you some experiments with helium, trying to probe the supersolidity of helium. So a phase that breaks both translational symmetry and this number of particles conservation, or this phase symmetry. So this is based on these experiments that are meant to measure the angular, the torque. The momentum of inertia of the helium. So what you have here is some torsion. You apply some force, some torque, and you try to, and then you look at the oscillations, like in a pendulum, that the period of oscillations depends on the spring constant. Here, this would be dependent on the momentum of inertia. So this is a measurement of the momentum of inertia, and the hope was that when you cool it, when you bring into a supersolid phase, then what happens is that the solid part will oscillate, but the liquid part doesn't, because it would be frictionless. So this is sort of a two-component approximation, where you assume that there is a superposition, a coexistence of a solid and superfluidity. And so you say, well, the solid will oscillate, but the superfluid won't. And so you should see a reduction in the momentum of inertia of this of the helium when you bring it into supersolid phase. Okay, so this is a sketch of how it looks like. So in the ordinary solid, you see that all the molecules follow this solid structure. Actually, I think this is a little bit counter sort of means, in the solid, you should have all the particles that are organized. But anyway, okay, so this is a sketch of saying that there should be some particles in a solid, that form a solid, while others are in a superfluid. And so this should lead to a reduction of the. Now, some preliminary experiments, I mean, this was from 2004, the original experiments have demonstrated such an effect. Actually, you see that even in the title, there was a sort of a question mark, say probable observation of a supersolid helium phase. And then 10 years later, they repeated the experiment with more accuracy, and they saw that basically no supersolid. So there was no, the signal was due to this reduction of this. The observation of the reduction of the momentum inertia was actually just due to other some other effects and some other experimental details. So there was no supersolid. So up to date, it is not clear whether superfluid helium can be found in a supersolid or not. But this was the supersolid phase was obtained recently in experiments with ultra-cold atoms. So actually, these are ultra-cold atoms of a particular type. These are ytterbium atoms that have a very large magnetic dipole, and so what you so there is here a competition between on the one hand some basically negative scattering length. So what does it mean is that here you use a Feshbach resonance so that the atoms actually attract to each other. So if you just had bosons that attract to each other, this would lead to an instability, right? The minimal energy state would be a state in which all the atoms collapse. All the atoms collapse in the same state. This would be the minimal energy state. If you had both fermions, then it's fine. You can have attractive fermions. Actually, we know that this is the physics of superconductivity. So that's fine because due to the Pauli principles, all the particles cannot collapse one on top of each other. But for bosons, if you had just attractive interactions, you would see a collapse of all the atoms collapsing on one side. But because here there are two forces, so there is an attractive force due to this Feshbach resonance, but there is also a repulsive force due to the magnetic dipole. Because you know the dipoles that are, when they are parallel, they're actually they actually repel. And so and because the forces have a different functional dependence, you can reach a situation in which on the one hand the bosons attract, but they do not collapse. And what they form are sort of structures that are known as droplets. And this phenomenon is known as a Rosenzweig instability. So Rosenzweig instability is the transition between, on the left-hand side, the bosons that just repel each other because they have, say, strong, the attraction is not strong enough. And when you increase the attraction, at some point there is an instability and they form these droplets. And the droplets are sort of a balanced state between, they minimize the energy between on the one hand, the attraction and the repulsion. And so you get a minimum of this size of the droplets. So the size of the droplets depends on the ratio between these attractive and repulsive forces. Is this clear? Okay, I hope so. Okay, now at least I can see some of you. Good. So this is an experiment, and in the experiment you see those droplets. Actually, in this case, you have a very strong confining potential in one direction, so that all the droplets form just in one direction. So this is a one direction. These are these red these red bubbles are the droplets. Okay, so and the droplets, they have a finite size, and you have many of them. You can consider it as a lattice. So this is not a lattice of single particles, but is a lattice of droplets. But as I have discussed before in the previous hour, this is the same. As I mentioned, we think of a lattice as just particles sitting on the side, but the quantum lattice is just some density fluctuations. So having a periodic density fluctuations means that you have a solid. As you can see, this is not a perfect solid, and it's actually sort of quite short, but it's still, you can consider it, if you had probably more bubbles, you could consider it really as a lattice. So what you have here is a lattice. Now, in the lattice, within the lattice, in each side of the lattice, there is basically a Bose-Einstein condensate, or maybe a superfluid. And then the question is, what about the phase? So each droplet has its own phase, but do the different droplets have the same phase or not? And if the droplets have the same phase, then we can call it a supersolid. Why? It's a solid because there are density fluctuations, and it's a superfluid because you have long-range coherence. Okay, there is a broken symmetry of the phase. And so this was the first experimental observation, how you measure the phase. So in order to measure the phase, what you do, you take your droplets, so this is shown here, and you release them. So you basically, you release the trap, there is the confining trap, you release them, and then all the atoms start to expand. And as we have seen in these matter wave interferometers, okay, this is what you obtain is interference fringes, and the interference fringes tells you something about the phase coherence between the different droplets. Now, here there was a caveat in these early experiments, which is written here. It says the principal interference, so the fact that you see an interference yield information about the nearest neighbor coherence. So the fact that there is an interference fringes actually just means that there is a coherence between nearest neighbors. This is not still sufficient to tell you that there is a coherence among the whole lattice. If you remember the physics of spins, let's say of ferromagnets, you know that the difference between a ferromagnet and a paramagnet is not the fact. So even in a paramagnet, you can have short range coherence. What you need in order to define a ferromagnet is the fact that you have all the magnets, the point in the same direction throughout the whole lattice. You need to have long range order. So also in this case, in order to call it a supersolid, it's not enough to have a coherence between nearest neighbors. That's quite simple. What you need to have is a long range coherence of the phase. You need to assume that all the phases throughout the whole lattice are the same. And this is already something that is more demanding. Now, what they say here is that the additional peaks, the fact that there is not just a single peak, but additional peaks corresponds to next nearest neighbor coherence. But so what I'm saying is that these early experiments showed that there was some coherence, but it was not enough to demonstrate that there was long range coherence, so that this was really a superfluid throughout the whole lattice. And this result was obtained very, very recently. It's in January 2021. So that's why it was not in the syllabus. It was not published yet, you know. It was not published when I prepared the course, but luckily enough, we can speak about it now. And so what you see here, this is an experiment, phase coherence in out of equilibrium supersolid states of ultra-cold dipolar atoms. So what they're now going to show is an experiment in which they show that there is phase coherence throughout the whole lattice. So how is this done? So what you do, you first prepare these droplets, okay? And the droplets, and at the beginning, okay, so you see, you change this scattering. So in a way that that you separate all these droplets, that each droplet is now separated. You wait some time, and when you wait some time, each droplet will acquire a different phase. Now, remember that the dynamics is the dynamics of the phase related to chemical potential. Because the different droplets have a different chemical potential, they acquire different phase. There is a e to the minus I mu t, which is different for each of the droplets. And as a consequence, each droplet will acquire a different phase. Then what they do, they sort of restore these droplets, they connect back the droplets. And what they ask themselves is, does the system acquire now a coherent phase? So what they do more, it's not just to show that at the beginning there was a coherent phase, which is nice. They also do some non-equilibrium dynamics in which they let first the phase decohere, and then they combine them together and try to reach, to go back to this phase coherent state. And this is shown here. So in the first, so there are two stages. What you see here is delta phi. So delta phi is the sort of the average distribution of the phases. So you measure the phase of each of each of the droplets separately, and this is shown here. You see that after some time, all the phases are randomly distributed. Okay, so think of this, each of these points, you can think of it as a different droplet, or maybe a different, or the phase difference between two droplets, and you see that they are all scattered throughout the whole with all the angles. Okay, so yes, so at the beginning there was some phase coherence, but then as they, so this is first stage. Okay, stage number one is a stage in which each droplet acquires a different phase and hence all the phases decohere, and you see that they are randomly distributed with 0 and 2 pi. Then there is a second stage, and the second stage they combine them together, And when you combine them together, you see that now the phase difference now goes close to zero, you know, is very much reduced. And this is shown here in this. After some time, you see that now all the phases have chosen, actually this is the phase difference. So the phase difference is now all close to zero. You know that the absolute phase, there is no way to compute the absolute phase, but you can compute the phase difference between different droplets. And you see that now all the phase differences has become close to zero. And so you have now went back, you have now moved back to the supersolid phase, in which these droplets are accompanied by a coherent phase. Okay, so you see that both processes, there is a process of dephasing, where all the phases acquire different value, and the process of rephasing. Actually, I was very happy about this article because they cite our work. So in this is a work in we have discussed two one-dimensional. We have considered two one-dimensional superfluids that merged together, that are merged together. So this was not a supersolid, this was just a superfluid. So there was no density ripples, but in a sense it was similar because it was a one dimension. So in one dimension you can think of it as as if you had a phase, as we have discussed in these matter waves experiments. So it's not exactly the same, but still I was happy because I cited our work. Okay, so you can see that you can first of all demonstrate a supersolid. And the second, you can even destroy, you can even play with the phase. You can destroy the phase and then build it back. Okay, so that's what I wanted to show you today. Do we have a presentation do we have a student presentation today?
Yeah, I prepared that.
Yoni. Okay, very good. So let me stop sharing my screen. If you have questions, if not, we can let Jonathan. Jonathan, you can start sharing your screen.
Okay, 1 second. Okay, can you let my iPad check? I connected a new.
I think everyone can.
Everyone can check.
Yeah, everyone can share your screen. Yeah.
Oh, thanks.
Okay, so let me spotlight your computer.
That's a spoiler of everything.
Okay. Okay, so Yoni, the stage is yours. So Yoni today will speak about we have spoken about one experiment on many-body localization, and Jonathan is going to present another experiment actually by the same group by looking at different type of many-body localization. So
thanks. So I'll present this paper about many-body localization in 2 dimensions, which is an experiment in cold atoms, like we've seen in week 4, in lecture 4, but this time with bosons. So some of the experimental setup will be pretty familiar, and we will see what is new and what they realize. So first, let us discuss many-body localization. So in class, we started with single particle Anderson localization. So Anderson found out that disorder causes the wave function to remain localized. A wave function which is initialized in some region or area in space can remain in that region forever, depending on the disorder. So for dimensions 2 and smaller, actually any amount of disorder causes localization, so there is always localization in this case. And in dimension 3, there is some critical disorder from which above there will be localization, and below there will be diffusion and no localization. Now, in many body systems, the behavior is more complicated. So the difference is the interactions in the many body system between the particles. And these interactions allow thermalization. So on the one side, we have localization, and on the other side, we have thermalization, where the wave function explores all the Hilbert space, and interactions move us towards this thermalization side, because they let the wave function evolve and explore more states. So a simple model toy model for studying this phase transition is the Bose-Hubbard Hamiltonian, which describes particles in a lattice. So there is one term, this J term, describing the hopping. There is an interaction term U with the particle operators, and there is on-site potential, which this is the Hamiltonian they use in the experiment, in the paper, they realize in the experiment. So in their experiment, delta I will be random. So this will be, the variance in delta I will be the amount of disorder. And there is also a constant on-site potential just to trap the atoms. So this is really what we are studying, how the disorder and the interactions affect this, whether the system is many-body localized or is it thermalized, with the general expectation that disorder drives us towards many-body localization and interactions drive us towards thermalization. So the actual experiment is an optical lattice like we discussed. So there are two lasers opposite to each other can create a standing wave pattern, which is like a periodic potential in which the atoms are trapped. And if we have more than two lasers, we can really create many patterns. And this group manages to create complicated patterns of periodic potential. So this is one picture of a two-dimensional square lattice, which they will use in this experiment. So the atoms are trapped in this minimum, and this is really like the atoms in a solid, like the periodic thing that would be in a solid. And the system that they will use is atoms of 87 RB, I'm not sure about the name, at unitary filling, which is a Motin solid. And they will modulate this periodic potential to have some randomness, so that will be the disorder. So on top of this periodic lattice potential, there will be fluctuations which they control, so they seed some random distribution, and they control the amplitude of this randomness, and that will be how much disorder there is in the sample. So the experiment looks like this. Everything, they can freeze time by really lowering the potential. So initially, the on-site potential is very deep, and so the atoms are trapped and they are not moving, and when they decide, they can raise the potential a little bit and allow hopping and start the time evolution. So they can prepare the sample, and then
Jonathan, I would say the opposite. So I mean, when the potential is very high, then the particles are freezed, and when the potential is small, they can hop from one side to the other. So,
yeah. I had in my mind like the okay. So
the minima, the wells are going down. Right. But I mean, physically, what they do is they have a stronger laser intensity in order to trap the atoms, and a weaker laser intensity to let them move.
All right. So the absolute value in the they start from a very big absolute value, and so So in order to test the localization, they prepare the atoms. They have some cloud of atoms, and they can do some manipulation to remove 1/2 of this cloud. And they remove the right half of this cloud and then lower the laser and start the time evolution. And the test whether the system is localized or not is whether the left side whether the distribution will start being homogeneous, whether the right side, which is empty, will start filling again. So here we see two extremes of this experiment. In the left, there is no disorder, and after long enough time, the distribution returns to be homogeneous. And we lose the memory that initially we had only filling in the left side. So that's without disorder, there is no localization. While in the strong disorder, as we let time evolve, the right-hand side does become filled, the atoms diffuse, but they reach some steady state, which is not homogeneous. So even after very long times, there remains some imbalance, and we can see that we started from an inhomogeneous wave function. It never became homogeneous.
Yes, you explained it very nicely, and also I appreciated what you said that about the memory. So this is very important. That's something that I didn't stress enough. But the many-body localization, many-body localized phase is a phase that, as you mentioned, has memory of what happened before, and that automatically means that it's not an equilibrium. It's not an equilibrium state, right? The assumption of an equilibrium state is that you have a well-defined temperature. Then that's what you have. You know, all the state is defined by the temperature, not defined by the history. So the thermalizing phase is such a phase, while the many-body localized is a phase that you cannot, you have always memory of what happened before, and so it's not an equilibrium. Although the Hamiltonian is time independent, it's not an equilibrium phase because you always get stuck somewhere depending on where you started from. So you cannot describe it in terms of a temperature of an equilibrium state.
So to quantify this filling of the right side more quantitatively, we define this imbalance. So that it's the ratio between the density at the left side compared to the right side, and look at its evolution over time. And here in the plot we see different plots for different amounts of disorder. And we see that around between the light green and the light blue, there is some phase transition, there is a qualitative difference. The imbalance ratio stops to drop all the way to 0. So when the imbalance is 0, we come back to an homogeneous distribution. And between these two values for disorder, we see that there is a steady state value of the imbalance, which is not 0. And as we increase the disorder, this value goes up. And also the time so they feed this data to a decaying exponent and take the decaying time. And also this decaying time reaches some saturation. So that's the inset. The more disorder, the more it takes, the longer the imbalance reaches the steady state, but it reaches some saturation. So the imbalance stops to drop. And looking more closely on this phase transition, we can look at the imbalance after long enough time. So we've seen that the dynamics stop, the maximum decay constant is around this 70 taus. Taus is some time scale related to the tunneling, to the hopping parameter. So after this amount of time, basically the dynamics stop for all values of disorder. And we just take a snapshot of the imbalance ratio after this very long time. And in this plot, we can see more clearly the phase transition between localized and thermalized. And here the value for the phase transition, for the critical value for the disorder is around 5.5, where the imbalance stops to balance. They look at a similar kind of measure, not this imbalance, but some higher resolution, looking at the density deviation across the x direction. So the x direction, the right hand side is positive x, the left side is negative x, and this is also just looking whether we reached a homogeneous distribution after a long time or not. And this measure gives similar result for the critical disorder, slightly different, but with the error bars, it's pretty much the same. The authors do mention that around the transition, it is hard to see exactly what is going on, because they expect that around the transition, there might be slow evolution of the wave function. So it might reach equilibrium if we wait even longer times. So actually this imbalance over here might do drop to zero if we wait long enough, but the experiment is also limited by how long we can keep these cold atoms and not have them leak towards higher state. So currently that's the best they did in this paper. Another thing to look near the transition is to look for critical phenomena. So one is a diverging length scale. So looking at the localized phase, again after a very long time, after this 190 tau, we look at the density across the towards the right direction, towards the empty direction, and see how it decays. And for a small amount of disorder, the distribution is homogeneous around this point, so it's flat. And for the localized phase, the density decays exponentially. And they fit this to a decaying exponent and extract this length scale of the decay. So lambda is 1 over this length scale. And if we plot the length scale, we see this divergence near the phase transition. So as we go towards the critical value of disorder, the length, this length scale diverges. So the last figure in the last slide here is actually the effect of the interactions on the transition. So in order to control the interactions, what they do is play with the particle density. So if we had only one particle, there would be simply no interactions, because there isn't, it doesn't have partners to interact. So here they took 1/4 of the particle density and thus effectively reduced the effect of interactions. And the expectation is that without interactions, we go back to this single particle picture where there is always localization in 2D. So that's in the inset, these lines, these squares. This is just numerical calculation in the single particle case. So in the single particle case, there is always disorder starting there is always a localization, starting from the smallest amount of disorder. And when they lower the interactions, they decrease the particle density. Indeed, the critical disorder became smaller. So you need less disorder for localization if you lower the interactions. Okay, and that's basically it. So just maybe the bottom line is that this simulation this experiment allows to explore this Bose-Hubbard model which is would be very hard to calculate numerically. So here, for the single particle, they can calculate numerically because the Hilbert space is not so large. But once we have many particles in 2D, effectively right now, it is impossible to calculate numerically. And this experiment really gives us an insight of how this Hamiltonian works and whether the current theory about many-body localization to confirm predictions and stuff like that. And it's a really nice thing. So thank you for listening.
Thanks, Jonathan. Very, very nice presentation. Okay, so if unless there are questions, then we will reconvene next week for the next lecture of the course.